So we're going to start our talks on the cardiovascular system. First lecture we'll deal with blood, heart, and circulation throughout the body. And then the next lecture we'll build on that with cardiac output and blood flow and blood pressure. Okay, so we're going to we'll focus on blood, what's being transported in the cardiovascular, then the pump of it, and then we'll talk briefly on the blood vessels and the circulation of it. So what's the function? What are the functions of the heart? Kind of the main transportation, right? The heart allows the blood, pumps it around the tissue because all those tissues, they got to have oxygen to do cellular respiration, and they also need the nutrients so they can do cellular respiration. And then vice versa, it needs to take the waste away from the tissue. Okay, so we're transporting all these things, not just the gases, but we'll see quite a bit throughout the body, all the ions and so forth. So transportation, regulation, because we already talked about endocrine. We got hormones travel throughout the blood, and also we can help regulate temperature by bringing blood to the surface to cool us off, or to conserve it near the organs to retain the heat. And then protection, we'll talk about clotting and immunity, and we'll get more into immunity later on. So what's major components of the cardiovascular system? Okay. We got the pump. What's going to pump? What's going to provide the force to push the blood throughout the body? And that's going to be that heart, that four-chambered pump we got. Okay. And then the blood vessels are basically the highway onto which all the blood is going to flow out. So the pump provides the force to push throughout all these blood vessels. We got the arteries, it goes to the smaller arterioles, and then the capillary beds, and then venules and veins. So those are the carriers of the blood. The cardiovascular also works with the lymphatic system to bring much of the interstitial fluid back into the blood supply. So we'll talk a bit more on lymphatic tissue when we start talking immune system. So let's first talk blood in our body, roughly around 5 liters. Some larger individuals might have 6 liters up there, but roughly around 5 liters of blood. The blood leaving the heart, it's been to the lungs, so it is oxygenated. And then the blood returning to the heart through the venous system as deoxygenated. Now, it's not devoid of oxygen, but has less oxygen than when we say oxygenated blood. Okay, and what's making up the blood? Basically, about 55% is the plasma, is the liquid of the blood. Okay, the liquid portion. The other 45% is what we call formed elements. And they call formed elements not cellular, because not all of the formed element portions are cellular, like our platelets, okay, and our red blood cells we see here. These are not true cells, right? Unlike the white blood cells are actual true cells. So they call them formed elements because not all of it is cellular. Okay, some are fragments of cells, okay, or kind of like cells, but non-nucleated in the red blood cells. This just gives us a further breakdown of what's in there. You can see in the plasma, okay, most of it is water. Okay, we got proteins in there, and we got electrolytes, nutrients, the respiratory gases. That's all dissolved in that plasma portion. The formed element portions, we got basically 2 components. We got this little buffy layer here, and that's going to be all of our white blood cells, which we'll get to in more detail in immunity, but we'll talk briefly about them. And then the major component of the formed elements is those erythrocytes, those red blood cells. Okay, those are those carriers of oxygen. Probably learned about in anatomy. Okay, so it's making up about, this is only about 1% This will make up about 44%, right? And then the rest is the plasma. So of the formed elements, let's first look at erythrocytes. Okay, so you might have learned erythropoiesis, that's the formation of the blood cells of the erythrocytes. Okay, but they start out as nucleated, but as they go along, when they get to be mature red blood cells, they lack nuclei and organelles. Okay, you can think of them because the function of these cells is basically to carry the oxygen. And how do we carry our oxygen is with hemoglobin. Okay, the protein hemoglobin. So there is much, basically these are big bags of hemoglobin to carry oxygen. Okay, and their job is to carry oxygen, so we got to get diffusion. So you can see there's large surface area, all right, and also it's concave, so it decreases the distance gases must travel because we got to diffuse it in and out of the cell pretty rapidly. We're diffusing oxygen in and out, okay, and also CO2 that we will talk about. So here is that molecule that is making up the red blood cells. Basically a big bag of many of these. You can see 280 million molecules of hemoglobin per red blood cells. Okay, and its main function to carry oxygen and also CO2. You can see there are 4, 1, 2, 3, and 4. Okay, proteins or globulin proteins that make up the hemoglobin. Okay. And where these little hemes in here, this is where the oxygen, the O2, gets bound. Okay, bound to this iron heme. Okay, and there's 4 of them, so we can carry 4 molecules of O2 per hemoglobin, and we got 28 million molecules of hemoglobin throughout each red blood cell, and many millions of red blood cells, so you can see we can carry many molecules of oxygen. You see here's where oxygen binds, but we'll see carbon dioxide does not bind chiefly to the site. It binds on the globulin area. So here are the white blood cells. This makes up the little buffy coat. That little about 1% of the blood is made up of these leukocytes. Leukocytes being white blood cells. And these are the actual cells of the blood, right? We call them formed elements, but these are actual cells. You can see multinucleated or binucleated. They got the lobes, so they have nucleus. They can be classified. 2 major classification is granulocytes and agranulocytes. You probably learned these in anatomy, but the granulocytes, they have visible granules in them. You see kind of the granules here. So these are the neutrophils, the eosinophils, and the basophils make up the granulocytes. Okay, the cells with not granules, not visible granules, those will be the lymphocytes and the monocytes. Another formed element that makes up the formed elements of the blood, right, are the platelets. And these are not cells, they are fragments of a cell. So there are these megakaryocytes that reside in the red bone marrow. Okay. These are actual cells, big cells, very large cells, but what they do is they fragment, and the fragments are what we call platelets. So these are again formed elements. They are not cells, they are just fragments of a cell, and these are involved in the clotting of the blood, making those scabs we have. And we're going to look at that process in just a second here. So our red blood cells, they have a short lifespans. They don't go out in the blood and they're there for a lifetime. They get used up, they get old, and they will get basically broken down. So we have a process, hematopoiesis. Hematopoiesis is the making or production of the blood cells, continually produced. And like anything, as you get older, this comes less and less. Okay, but during the time, these cells are continually being made. The red blood cells, the white blood cells, okay, and they're made from a stem cell called a hemocytoblast, okay, in the red bone marrow, because that's where all our cells, our blood cells are being made. They get made in the red blood cells, put it out in the blood. We'll see some end up going for more maturation, but two major cell lines, this hematocytoblast, say this is one cell, this is our hematocytoblast here, okay, it can get made, okay, can do what we call differentiate, okay, this cell can basically become any blood cell, white blood cell, red blood cell, okay, megakaryocyte, it can become any of the blood cells, and once it differentiates, it can go to one line, the myeloid, okay, start down that pathway, or can go to the pathway of the lymphocytes, okay, that's the lymphoid line, all right, and then you can see the myeloid line ultimately will be differentiated into these other cells, okay, the only one that can't be made from this myeloid line are the lymphocytes. That would be here. We get B and T lymphocytes. Okay, but once this cell, this hematocytoblast, okay, the beginning stem cell differentiates to either here or here, this intermediate, okay, because this cell will further go differentiate further down towards one of these lines. It cannot go back, okay, the stem cell. So once we differentiate, okay, this cell could be made out to any cells, but once it differentiates to here, it has got to become one of these lymphocytes. Or if it differentiates this way, it becomes one of these, and those are the red blood cells, megakaryocytes, and the other white blood cells that are not the lymphocytes. Okay, so this is a continual process. This is happening throughout our lifetime. We're making these new cells and depending on what's going on in the body, if we have more infections, we're going to be making, right, more white blood cells to go fight the infection. Or if we go up into like the high elevations, we go up to Big Bear, okay, for long periods, you have low oxygen up there, you're going to need more red blood cells. So depending on what's going on, depends on what the production of these are. You can increase or decrease accordingly on what's happening in the body. So one of the key characteristics in health, right? Many times we have to give patients blood, right? If they lose blood, we got to give them more blood, okay? And so that's why this blood typing is important. We have blood types, okay? And your red blood cells, this is where you get your blood type, has certain antigens. You might have heard of antigens and looking at coronavirus. Okay, the virus has a certain tags on the surface. Okay, those are called antigens. These are just tags that are usually specific to a certain cell, and the red blood cells have these tags on them, or it has a lack of tags on them. Okay, so whatever tags are on a person's red blood cells determines on what their blood type is. So what antigens are on their red blood cells determines whether they are, we're talking about ABO system. Okay, there are two antigens we're dealing with here. Red blood cells can have what's called an A antigen, so just a tag on a surface that is different from a B antigen. Okay, so we have two antigens. If we're to see the blood, ABO, we can have, a person can have all A. Okay, their red blood cells would just have A. Okay. Or a person, so their blood would be A blood. Okay, person's blood cells may just have B antigen. Then they would be B blood. All right. Some people have, like your professor, have A and B on their red blood cells. So they have both markers on their red blood cells. So that is AB blood. And then there are others that have neither of these. Don't have A, don't have B, and those would be the O's. Okay? The O's are the givers of the world. The ABs, like myself, are the takers. And we'll see why this is in just a second. Okay, so that's the AB system. There is one other. If you guys have gotten your blood typed, you might hear negative or positive. And negative positive has to do with this RH, rheus antigen, found from the rheus monkey, also known now as antigen G. So if you hear antigen D, it's still the RH antigen, the rheus antigen. Okay, and so this is notated. Okay, if you do have the RH antigen, you are positive. Okay, you're whatever of this, AB, A, B, or O, and then positive. If your blood doesn't have the antigen, then you're negative. So for me, I'm AB. I have both antigens here, and I also have the rheus, so I'm AB positive. Okay, so I have all three antigens. So I am AB positive. Okay, because the blood type goes by what antigens you have. Okay? And this is genetically determined. Okay, so if mom and dad both have O, they can't have a baby that is A or B because both mom are O's, so they're going to have a child that is also O. So it's genetically determined. So this is how they can kind of figure out, hey, they can rule out some people on paternity tests because of their blood type, but only certain ones. All right, so the AB system here is just a visual. Okay, the different bloods. Remember, the blood type is by what antigen there is. The little circle here is the A antigen. The little spike is the B. So this cell only has B, so it is B blood. This cell only has A antigen, so it's A. And this one has both, so it is AB blood. And then there are the O's that have no antigens. Okay, neither A or B. Okay, could have the rheus because you could have O positive and it could have the antigen, the rheus antigen, the RH antigen, but it has, for the AB system, there is no A or B, so it is O blood. So your immune system, your lymphocytes, is ones we talked about, and we'll talk about more when we get to immune system. Those lymphocytes create antibodies, okay, and against foreign antigens, okay, antigens. So your body is very good. Your immune system knows your cells of your body. They know the different tags that your cells have, okay. But if it sees a tag that it doesn't know, an antigen that it doesn't recognize or recognizes as foreign, then your immune system will make antibodies against it. Antibodies, so then the immune system will go fight and destroy it. Okay, so that is what the antibodies, they will make antibodies against foreign antigens. Okay. Get antibodies produced with a common antigen. So this is if a person, so what's good about your system is your body knows if you are A blood, your body knows you have A antigen. So it will not make antigens against A. Okay? You will not have A antibodies. Okay? but you don't have the B antigen. Okay, so you can make B antibodies. So there would be person with an A antigen would have B antibodies. Okay, will not have A, so this is antibodies, will not have A antibodies because the A antibodies would attack the A antigens on that person's blood cell. Vice versa, if a person has a B antigen, they won't make the B antibody. The immune system of that person will not make the B antibody. Okay? But a person with B doesn't have an A antigen. So there is no cells that have this A antigen, and the immune system in a B blood would make the A antibody. Okay, this is antibody. I know, I wish there was a speller here, but okay. So here's looking what antigen, what blood types will have what antigen, and also what antibody they will make. Okay, and this is made spontaneous. It's just, if you have B, you are making A antibodies. This just takes place. Okay, it is spontaneous. It's not, you don't have to see this antigen. This is just taking place. Okay, because typically your body sees an antigen. If it sees B blood, it would make, okay, B antigen, or sorry, B antibodies. Okay, if an A person saw B blood. Okay, so let's look at this. Type A is A antigen. Remember, they won't make A antibody because A antibody would bind to their person's own cell. But there are no B antigens, so the immune system makes B antibody. Okay. Where vice versa, antigen B, this is B blood. There's no, all right, we're not going to make this antibody because this would attack that cell. But because there's no A, the B will make A antibodies. Okay? And this A, okay, would fight that cell. But this person doesn't have A antigen, so it can make A antibody. How about AB? AB has both, so its immune system says, no, I can't make antibody A and I can't make antibody B because then I would be attacking my own cells. And then neither A or B antigen, so this is O blood. Okay, and there is no antigen. So if I make A or B antibody, it can attack. All right, because there is no antigen on there. It's not going to bind to the red blood cells. So I can, for an O person, they can make both A and B. Or sorry, this is A and this is B. Sorry, A and B. Okay, can make both of them in this case. You can see this, where might this become a problem? So if somebody with O blood was given AB blood, okay, this is the patient, say O patient, this is the patient, okay, and they were transfused blood. They were given an IV and given blood, transfused in, and the blood was AB blood. When this person receives this blood, what's in their blood? Their blood has these antibodies, and these antibodies want to bind to A antigen and I want to B antigen. Okay, so if you transfuse this blood into this patient, the antibodies in this patient's blood are going to bind to these red blood cells. Okay, and that's a problem. Okay, and so the problem we have from the previous slide would be called agglutination. We'll see this in the next slide. But first, let's touch on the RH system. This is what gives you your blood type, your positive or your negative blood type. So you can be AB positive or AB negative, depending whether you have the RH or the D antigen. Okay? There is a difference between this and the AB system. Okay? In the AB system, these antibodies are made. You don't have to see a different blood type. They are spontaneously made. So if you have B blood, you are going to have A antigen. That is not the case with the RH system. With the RH system, okay, a person that is negative, okay, they don't spontaneously make the antibody. This person's immune system will only make the antibody if they are exposed to RH positive blood. Okay, so you got to see blood before you actually get the production of these antibodies. Okay, where the AB, this just occurs. All right, for the AB, if this person's O and they got no antigens, they're making AB antibody. They don't have to see A or B blood before the antibodies are made. But for the RH system, this RH negative person must see RH positive blood, and then they will start making. Okay, so that's after prior. Okay, there. All right, so we got two blood types. RH positive, that would be here. You got the antigen on the blood. RH negative. Okay. So if somebody is O negative, what do they have? They have no A and B and no RH, so they don't have either three of these antigen. On the opposite spectrum, somebody that is AB positive, they would have A, B, and the RH antigen. Okay? So where does this become a problem? Okay, there's one. Where would somebody see, besides a blood transfusion, where might somebody see somebody that is RH negative see RH positive blood? That is when we birth. Okay, because mom can be RH negative. So if she saw RH positive blood, okay, mom would start making antibodies. But what if mom is RH negative and baby is RH positive? Okay, in birth, what happens? It's lots of blood going around. You got baby's blood, you got mom's blood, lots of blood flowing around, and there could be a mix between baby's and mother's blood. Okay? For this baby, the RH positive baby's blood has that antigen. If baby's blood makes it into mom's bloodstream, now negative mom, RH negative mom sees that antigen on baby's blood, and mom will start making the RH antibody. Okay? Not a problem. For this baby, the first baby, okay? Not a problem. Because baby's already born. But what happens in the next subsequent pregnancy? Mom is RH negative, and say the second baby is also RH positive. What's running around in mom's blood now? She has the RH antibodies. Okay, and those antibodies can cross the placenta. Okay, they can cross over and get into baby's blood because they are small proteins. Okay, what if those antibodies get across to baby's blood? Those antibodies are going to bind to the Rh positive blood cells of the fetus. Okay, so first baby it's not a problem, but subsequent ones, okay, they can get what's called erythroblastosis fetalis. Okay, could pose a major risk to that baby. Okay, how do they prevent this? So there is a shot called Rogam. Okay, Rogam, if you're given Rogam, that will prevent mom is exposed to the Rh positive blood, she won't make the antibody. The Rogam will prevent her from making the antibodies. Okay, so many times my wife was Rh negative. So usually they're not going to blood type baby unless they absolutely need to, because it comes with the risk. So even whether mom's Rh negative, if you have an Rh negative mother, they're going to give you basically two shots of Rogam, usually one about 30 weeks and one right about delivery, because this is going to prevent Rh negative mom making the antibodies if she sees Rh positive blood. Okay, and then you wouldn't have a problem the next time around. Okay, do you need to do this for an Rh positive mother? No, they don't need a Rogam shot because they aren't going to make the Rh antibody. Okay, because they are Rh positive. They aren't going to make an antibody towards their own blood. So even if baby's positive, they're still not going to make the antibody because they have it in their own blood. So only Rh negative mothers are those that are going to, okay, need the Rogam shot. So what does happen when the donor bloods don't match? You give an O blood, an AB, you transfuse them with AB blood, right? Those antibodies are going to attack the AB blood. So you get what's called agglutination. You get this clumping, okay? And basically death of those red blood cells, okay? Donor blood can't contain antigens. So let's look at when we actually match donor blood with the recipient blood. Okay, recipient blood is type A, the patient's blood type A, the donor blood's type A. Okay, has the A antigen. For somebody that is type A blood, they are only going to contain, their blood only is going to contain antibody for B. Okay, this does not bind to the A antigen. This only binds to the B antigen. So if you put A blood into an A patient, they only have B antibody. There is no binding of the antibody to the red blood cells. Whereas now we got type A blood, we're donating, but this person is type B, the patient, the person receiving the blood is type B. And type B blood would have the A antibody. Okay? And the A antibody would bind to that antigen. So you put this blood in, this antibody's in the recipient of the patient's blood, you're going to get binding and you're going to get what's called agglutination. Okay? This clumping of these red blood cells. And you can see typically the red blood cells, when you get the smaller vessels, okay, they clump up and they can constrict, cut off blood supply to those. Okay, it could be very painful, okay, as long as you can get the blood back through, but also could cut off some blood supply too. And you can see how this, with that Rias portion could be have drastic effects on the fetal development of a baby. And then in a patient, you can see transfusion patient, what the effects could be also. This just kind of cheat sheet showing you which blood types can be given to who. And so let's look at, because remember type O. Type O blood has no antibodies, or sorry, no antigens on it. Okay, so type O blood, if you give it to any of these AB, okay, you can be fine because there are no antigens on here. Even though these bloods have antibodies, there are no antigens on this type O blood, so none of these antibodies will bind to this type blood. Okay, so this type O are basically the universal donors. Well, type O plus negative, right? Because negative means there's no D antigen, so this type of blood has no antigens on it, so there are no antibodies that can bind to it. Even if the blood have antibodies, they're not going to bind to these blood cells. So a type O negative is the golden seal of blood because they can be given to any patient. You can see AB. What do AB patients or people have? No A or B antibodies, so they have no antibodies that are going to bind, so they can take any of the blood. They can take AB, O, they can take all the blood. So an AB positive can take anybody's blood because they don't have the antibodies. So we've seen agglutination kind of is like a clotting, and we definitely don't want that taking place in the blood. But let's look at an instance where we do want blood clotting. Because when you cut a vessel, you cut your skin, you start bleeding. What's happening? You've cut into one of the vessels. Do you want to keep bleeding out? No, you want to basically put a plug in, right? And then heal that area from the damage. Okay, so that's when you want blood clotting. Okay, and what's going to happen when you break the lining? Endothelial, that is the epithelium that makes up the blood vessels. Okay, one thing is you're going, when we talked about vasoconstrict, meaning say the blood vessel is this big, would you want the blood, lots of blood to be flowing through here after you've cut it? No, you want to prevent it from flowing through. So you would get it, you vasoconstrict, make the blood vessel go from big to smaller. That is vasoconstriction. So that is one thing that is happening. Okay, and then we're going to form platelet plug, kind of basically that scab. It's going to form over to prevent the blood from continually to flow out. Okay, and what do you do when you hold on, when you get a cut? You punch it down, because what are you doing? You're constricting the blood through that vessel. So you're cutting off the blood so you prevent it from keep flowing through. Okay, and after we make the plug, we're going to make it stronger by making this fibrin web. Okay, to keep the plug solid and prevent it from getting taken away by the blood flow. Okay, so those three things are happening. So let's take a look at. So in an intact vessel, okay, we got platelets. Platelets are going to be those that make that platelet plug. Okay, but in an intact blood vessel, we don't want these platelets making a plug. So there are several factors that keep this from taking place. Okay, when we get a cut, we want to vasoconstrict, but in an intact blood vessel, we want the opposite. We want vasodilation. We want it bigger. Okay, so the blood vessels, the endothelial cells of the blood vessel, that are these here. These are those endothelial cells. Okay, those make the lining of the blood vessels. They secrete these factors, PGI2 and NO, nitrous oxide, and prostaglandin I2. These both cause vasodilation and also prevent these platelet cells from aggregating, okay, to make a plug. Okay. Also on the blood vessels are the CD39. Okay, this is an enzyme that breaks ADP to AMP, because ADP, we will see, promotes aggregation of these platelets, and at this point we don't want that taking place, so the CD39 keeps the ADP levels low. Let's look what happens when we damage the blood vessel. Okay, damage the blood vessel. Now we want these platelets to aggregate. We want vasoconstriction. Okay, and so in a broken blood vessels, the platelets are exposed to this layer here. Okay, platelets stuck to the collagen. Okay, they get stuck to this collagen, this layer that is below the endothelium, because this endothelium has been cut. Okay, now it is open, and we get this reaction takes place. Okay, this platelet reaction. Platelets start secreting ADP, thromboxane A2. Both of these activate these platelets. Okay, unactivated, they're round. Now they're star-shaped. Okay, they get activated and they bind, and then that promotes aggregation. ADP promotes aggregation of more and more platelets, kind of like a positive feedback, bringing more and more platelets in. More and more platelets, more ADP, okay, and we create this plug. They get this aggregation here, okay, and get further layers. So now we've plugged up this cut in the blood vessel. Although it's still not strong enough, if this was a very high flow vessel, that plug can still get washed away. So we do what's called fibrin formation. You're not going to need extrinsic and intrinsic, that's too much for us. But basically what's happening here is we're laying this fibrin, that's the green stuff here, mesh-like network. Okay, this makes this platelet plug, gives it much strength. So if this is high flow, it won't wash it away. It'll keep it plugged in there. So that gives us our vessels, and as the cells repair each other, then that scab can go away. Alright, so we've finished with the blood. Let's look at basically the rest of the cardiovascular system. That's going to include our heart, right, and then all our vessels. We're going to focus mainly on the heart here first, and then we'll come back and at the end we'll finish with looking at the vessels. Okay, there are three types of circulations. We're going to be looking at pulmonary, systemic, and coronary. Okay, and the blood that these carry. Okay, oxygenated, that would be noted by the red. Okay, when we're looking at the system, and deoxygenated blood would be with the blue. And when you're talking deoxygenated, it means it's not void of oxygen, but it has less oxygen bound to it as the oxygenated blood. Okay, so let's look at the pulmonary and systemic circulations, and then we'll get into the big details of the heart. Okay, we have the right side of the heart and the left side of the heart. Okay, the right side of the heart's function, okay, blood's returning to the right side of the heart. We can kind of go through the flow of blood. If you remember from anatomy, just blood returns to the right atrium, okay, gets pumped to the left, or sorry, right ventricle. The right ventricle pumps up to the lungs. Then the blood returns to the left atrium, the left ventricle, and then out to the aorta and to the rest of the body. Okay? the right side. Okay, the right side here. Right? This deals with the pulmonary circulation, because where are we taking the blood? From the right side, we're bringing the right ventricles, bringing it up to the lungs, to the pulmonary circuit. Okay, so pulmonary circulation, deal with the right side. That's the blood vessels that go from the right ventricle to the lungs and then back to the left atrium. Okay, and systemic. Systemic is basically the vessels that carry the blood from the left side of the heart to the tissues. Okay, and then back to the right side of the heart. So you got most of the arteries and veins, okay, of the body are part of the systemic circulation. Okay, pulmonary is just dealing with those that bring it up to the lungs and then back to the heart. Systemic is out to the body and back to the heart. So this is the bigger component. This has got many blood vessels, okay, and this is where the left side of the heart pumps out to. Okay, so one of the not special, but one unique is the coronary circulation. Okay, because you'll see the blood getting pumped into the aorta is going out to the rest of the body, and the first branch off the aorta actually brings the blood to the coronary arteries. Okay, the coronary circulation, because the heart is going to get the oxygenated blood first. Okay, because pulmonary, we bring the blood up, get oxygenated, bring it back to the left, and then out the oxygenated blood, it gets pumped out to the different tissues. First branch here is part of the coronary circulation. So coronary circulations are the arteries, okay, the vessels that are supplying the blood to the heart, the oxygenated blood, and then bringing it back to the heart. Okay, includes the arteries, coronary veins, and then that coronary sinus, okay, where all the blood gets pulled back and then back into the heart, back into the right atrium. So the heart's an important organ. It's got its own tough membranous sac, the pericardium, that wraps it. Okay, it's a serous membrane in that there is a visceral layer that lines the heart. Okay, and then the parietal layer that is outer, and there is even a thicker layer, connective tissue, okay, around the serous membrane. Okay, that makes the pericardium. Okay, it keeps the heart from getting enlarged. It also has that serous fluid, so it reduces friction, because remember, this heart is going to be beating, so it will be moving around. So the pericardial fluid reduces the external surface, keeps the heart from rubbing against the pericardium. Okay, prevents that friction. Pericarditis, that would be inflammation. Okay, if this starts getting inflamed, it will start pushing on the heart. My father actually had this at a young age, at 30, and he lost about a third of the heart muscle. So he's been living most of his life with 2/3 of the heart muscle around. Okay, but pericarditis, inflammation of that pericardium, and it will put pressure. Okay, this gets inflamed, it's going to put pressure on the heart. It's going to make this area smaller for the heart. So let's go back. Let's look closer at these 4 chambers. Okay, there are 4 chambers. We got 2 atriums, the right and the left, and 2 ventricles, right and the left. Okay, the atriums, are function is basically to receive the blood coming back to the heart, and then to pump the last bit of blood to the ventricles before the ventricles contract. So the ventricles are pumping out of the heart. For the right side, again, we're going to the lungs. It's the pulmonary circulation. And then for the left side, we're going out to the systemic, out to the aorta. Okay. Again, the blue, that's deoxygenated blood, because this is blood that's gone to the tissue. The oxygen's been released to the tissue, and it's returning back. And now it's going to head to the lungs to get oxygenated, turn into the red, the oxygenated blood. Okay, now we got oxygenated, we can pump out to the rest of the body. Okay, but that's the flow of it. And we're going to go right atrium, right ventricle, out to the pulmonary, out to the lungs, and then back to the left atrium, left ventricle, and then out to the aorta. So again, the heart's made up two atria, two ventricles. Atria is going to be pumping into the ventricles, and then the ventricles out to the vessels. So if you look at these muscle here, it's kind of basically made into a sac. So what's going to happen when these chambers contract, the muscles of this chambers, if the muscles loop like this, when it contracts, it's going to say, when it contracts, the size of it may be much smaller. Okay, and when we create the smaller space in this chamber, we are increasing pressure, and pressure is going to push the blood. So when we contract the atriums, we push, pressure increases. If the ventricles are relaxed, the blood's going to be pushed in there. And then when the ventricles contract, pressure increases and the blood's going to be pushed out. Okay, to ensure, so the walls of this, we got septum, prevents blood going from here, pushes it out to there, but also we have these valves. These valves are going to ensure that the blood goes in one direction. Okay, goes out the way it's supposed to go. Okay, so we got, probably remember these valves from your anatomy days. You got the right AV valve or the tricuspid valve. You got the left AV valve or the bicuspid valve. All right, these are between the atrium and the ventricle. Atrium and ventricle. Whereas you have the semilunars. This is the pulmonary semilunar because it's going out to the pulmonary trunk. So it's between, this valve is between the ventricles and the pulmonary trunk. Okay, pulmonary arteries. And then where's the aortic semilunar? Is between the left ventricle and the aorta here. That's the aorta. Okay, so these are going to ensure that the blood flows, okay, goes from right atrium, right ventricle out to the pulmonary trunk, and then back to the left atrium there, to the left ventricle, and then out to the aorta. Ensures that it doesn't go from, we don't want the blood going from the left ventricle back into the left atrium. We want it flowing into the aorta, right? And when this ventricle contracts, we want the blood flowing into the pulmonary trunk, not back into the atrium. Okay? So remember, this blood is going to be flowing from high pressure to an area basically of lower pressure. So pressure is what's going to be moving the blood, and that contraction of the heart increases pressure in the chamber and then can cause the pushing of the blood. Okay, but the valves are here to ensure one-way flow. Okay, a little better setup. You can see these are the AVs. Okay, that's the left. This is the right. Okay, and then there are these semilunar valves. Okay, if you remember, the AVs have these chordae tendineae with these papillary muscles, chordae tendineae with the papillary muscles. Okay, ensures one flow. It is the pushing, the pressure, the blood trying to push back against them will actually close these valves. So that's what's going to be closing the valves. The blood trying to rush back against them will actually shut these valves. But it ensures when this ventricle contracts, the blood's going to try to push back here. It gets shut, so then the blood can only get pushed into one direction, into the aorta. Okay. Again, the AV valves, what are they? They're preventing backflow into the atrium. That's their function. Okay, because when this ventricle is contracting, this atrium is relaxing. So pressure is low here and pressure is getting high, so blood would want to flow back towards the atrium. And so this is what these valves are ensuring, that this does not take place and that the blood is pumped into the pulmonary trunk, or for the left ventricle, this is ensuring that the blood is pumped into the aorta. So for the heart, we got the semilunar valves. That's our second set of valves. We've got the AV and now the semilunars. We're looking here. Okay, there's the pulmonary, and the aortic would be wedged right in there. Be very similar to this little cusp. So they have these little cup-like leaflets. And so what these valves are preventing is backflow into the ventricles, because remember, blood is going to flow from an area of high pressure to low pressure. Okay, at a certain point, these ventricles are going to relax. After they contract, they relax. And what's going to happen? Remember, contraction causes greater pressure. Relaxation is going to cause reduction of pressure in these ventricles. Okay, and when you go to the doctor, what happens? You take blood pressure. A lot of times they take blood pressure. What is it? Yeah, that 120/80. There's 80 millimeters of mercury of pressure in your vessels when your heart's at rest. So there is still pressure in these vessels here. Okay, that blood being pushed out here extends the wall and causes pressure on these vessels. So there is it's not low pressure. There is still a substantial amount of pressure in these vessels. So when this ventricle goes to relax, where do you think this blood in these large vessels would want to go? Yeah, it would want to try to backflow into the ventricles. So that is what these valves, the semilunar valves, are doing, preventing the backflow of the higher pressure blood in this vessels back into the ventricles. Okay, and those are the semilunar valves. Okay, so what happens when the AV valves? To the AV valves, when ventricles contract, there's pressure increasing in the ventricles, and as the ventricles are contracting, the atriums are relaxing. So low pressure here, high pressure here, blood's going to try to flow back into the atrium, and we don't want that to take place. So that is when these valves close shut, the AV valves. And then for the semilunars, okay, semilunar valves are going to be open in that case. But we're going to get into this whole cardiac cycle and when it's taking. The atrial contraction, though, is going to close the AV valves. Okay. Ventricular relaxation, what happens? AV valves will open, but what happens is semilunar valves. Okay. Semilunar valves are, pressure is low here. There is higher pressure out in this vessel. Okay. In this case, it's the aorta, and blood's going to try to run back, and so that's when the semilunar valves close. The other thing about when these valves are closing is this is when you get your heart sounds, the lub-dub. When you go to the doctor, you hear, listen on the stethoscope, you hear lub-dub, lub-dub. Okay, there's two sounds to the heart beating, and those are the valves shutting. Second one is the semilunars. The first one is when those AV valves shut. So when those ventricles contract, shuts the AV valves, that's your first sound. And then when the ventricles relax, okay, get big again, in relaxation, that's when the semilunar valves and give you that second heart sound. Another anatomical feature, this goes back to the valves, but this fibrous skeleton, okay, basically is between, this would be the ventricles down here, okay, or down here. What's lopped off is the atrium. So this fibrous skeleton sits between the atrium and the ventricles, and it serves several functions. Okay, it's basically the connective tissue for where the four heart valves sit. It's also the origin and insertion for the heart muscles, because the heart muscle basically does this loop-like pattern up. Okay, starts here, moves back, and ends there. Okay, so we kind of have this sac type muscle. So when it contracts, it makes the chamber smaller. And then one other key factor is it acts as an electrical insulator, because we're going to be spending a time about the electrical properties of the cardiac muscle, the action potentials of it. All right, and so this insulates the atrium from the ventricles electrically. Okay, this is going to be a key component on how the heart, the way in which the heart beats.